What if I told you the most fundamental thing we think we know about our universe, that it's everything might be wrong? We see it expanding, galaxies rushing away from each other faster and faster. We ask, expanding into what? The usual answer: nothing. Space itself is expanding. It's a concept that bends the mind, right? But what if that expansion isn't happening in a void? What if our universe is pushing against something else? Something unseen, undetected until now. Prepare yourself, because a recent, almost accidental discovery, powered by one of the world's most advanced cloud networks, Microsoft Azure, might have just given us the first tangible hints of what lies beyond the edge of everything we know. And folks, this isn't just another theory, it's data. Data that's sending shockwaves through the world of cosmology, forcing us to question the very nature of reality. Could this finally explain mysteries that have haunted astronomers for generations? Or are we standing at the doorway to a completely new kind of physics? You see, for decades, astronomers have been wrestling with anomalies, weird gravitational pulls, galaxies behaving strangely, and the biggest puzzle of all, cosmic acceleration. Something invisible, something we call dark energy, seems to be acting like an anti-gravity force, pushing the universe apart at an ever-increasing rate. It makes up nearly 70% of the universe's energy density, yet we have almost no idea what it actually is. It's one of the biggest blank spots on our map of reality. A team of astrophysicists decided to tackle this head-on. They weren't just trying to refine existing models, they were aiming for something audacious. They wanted to simulate the universe's boundary conditions, the fuzzy, theoretical edge where our understanding of spacetime frays. Their goal: to find clues about dark energy, maybe even figure out if this cosmic acceleration is forever, or if it might one day slow, stop, or even reverse into a big crunch. This wasn't your run-of-the-mill simulation mapping galaxies like dots. No, this was a deep dive into the quantum realm, using mathematical extrapolations built on our most advanced, albeit incomplete, theories of quantum gravity and cosmic inflation. The moment right after the Big Bang, when the universe supposedly ballooned incredibly fast. They were trying to model the behavior of spacetime itself at its most extreme limits. Think of it like trying to understand the ocean not just by mapping the currents, but by studying the way water molecules behave right at the surface, under the influence of wind and atmospheric pressure. They wanted to see if the fabric of spacetime itself held a hidden signature, a pattern that could explain why everything is flying apart. To do this, they needed computational power on an unimaginable scale. Modeling the quantum behavior of even a small patch of spacetime is complex. Modeling the edge of the observable universe pushed the boundaries of possibility. That's where Microsoft Azure stepped in. We're talking about a simulation dataset involving over 50 petabytes of information. Let me try to put that into perspective. A single petabyte is 1,000,000 gigabytes. Your typical high-end laptop might have a terabyte drive, 1,000 gigabytes. So, 50 petabytes. That's like the storage capacity of 50,000 high-end laptops, or millions upon millions of DVDs, all crunching numbers, simulating the quantum dance at the universe's edge. Azure's cloud network, a vast interconnected web of computing resources, was the only way to handle the sheer volume of data and the trillions upon trillions of calculations needed. They ran the simulation. They watched virtual particles pop in and out of existence near the model's boundary, expecting them to behave according to known quantum field theories. They expected to see patterns related to vacuum energy, maybe some subtle quantum fluctuations influencing the expansion. But that's not what they found. As the simulation pushed towards its limits, something completely unexpected emerged from the noise. The numbers started showing resistance. Virtual particles reaching the simulated edge didn't just zip along. They experienced a subtle drag, a kind of friction that couldn't be explained by any known physical law. It wasn't vacuum energy. It wasn't standard quantum fluctuations. It didn't match any phenomenon within our current standard model of particle physics or general relativity. Imagine blowing up a balloon. You expect the rubber to stretch smoothly outwards. But what if, as it expanded, certain parts of the balloon seemed to encounter resistance, like they were brushing against an invisible, slightly sticky surface? That's what the simulation was showing. It was as if spacetime itself, as it expanded, was interacting with something outside the model. The team, led by the meticulous Dr. Emily Chen, initially suspected bugs, glitches in the code, errors in the data interpretation. This is standard scientific practice. When you see something extraordinary, your first assumption is you've made a mistake. They reran the simulation hundreds of times. They tweaked parameters, swapped out algorithms, stress-tested the code on different parts of the Azure network. They tried different starting conditions for their virtual universe, explored alternative interpretations of quantum mechanics, even plugged in modifications to Einstein's theory of general relativity. The result, the anomaly persisted. It was consistent, reproducible. It wasn't a glitch. It was a feature of the simulation, reflecting something deep within the mathematics modeling the universe's boundary. Dr. Chen famously described the feeling as watching simulated waves hitting an invisible shoreline. The energy, the momentum of the expanding universe in their model, wasn't just dissipating into nothingness. It was interacting, transferring energy, behaving as if it was encountering a medium beyond its own confines. The mathematics pointed towards something previously confined to the realm of highly theoretical, almost science fiction concepts, a higher dimensional field. The analysis revealed traces of what physicists call bulk resistance. This term comes from theories exploring extra dimensions, the idea that our familiar reality of three spatial dimensions plus time might be just a small part of a much larger, higher dimensional space, often called the bulk. This resistance wasn't uniform either. It varied depending on the direction of expansion in the simulation. In some directions, the drag was stronger, in others, weaker. This suggested that whatever exists outside, our universe isn't just a smooth, featureless void or field. It has structure, a kind of cosmic topology. It was less like expanding into empty air and more like pushing against a vast, complex, subtly textured surface. And then it got even weirder. The patterns of this resistance weren't just directional, they showed periodic fluctuations. These fluctuations looked remarkably like wave interference patterns. Imagine dropping two pebbles into a pond. The ripples spread out and interfere with each other, creating complex peaks and troughs. The simulation suggested that our expanding universe might be generating ripples in this external something. And these ripples were bouncing back, interfering with the expansion itself. Our universe wasn't just pushing against something, it was creating waves in it, and those waves were influencing us back. Host shifts tone slightly, leaning in. This is where the story takes a sharp turn from unexpected anomaly to potentially paradigm-shattering revelation. The results were so strange, so outside the mainstream, that the team knew they needed another perspective. Someone who wasn't afraid to think outside the conventional four-dimensional box. One name kept coming up: Dr. Lisa Randall. Dr. Lisa Randall, a renowned theoretical physicist at Harvard, has spent decades championing some truly mind-bending ideas, particularly the concept of Braneworld cosmology. These ideas, rooted in the complexities of string theory, which itself posits extra hidden dimensions, were often seen by the mainstream as mathematically elegant but likely untestable speculations. The core idea: our universe, everything we see, touch, and measure, all of spacetime, might exist as a four-dimensional membrane, or brane for short, floating within a much larger, higher dimensional space, the bulk. Think of it like this. Imagine you're a two-dimensional creature living on a vast sheet of paper. You can move forward, backward, left, right. That's your entire universe. You might not even be able to conceive of up or down. But your sheet of paper, your brain, exists within a three-dimensional room, the bulk. Now, according to Randall's theories, most forces and particles like light, electrons, the stuff governed by electromagnetism, and the nuclear forces are stuck to our brain like drawings on the paper. They can't leave our four dimensions. But gravity might be different. String theory suggests gravity might be mediated by particles, closed strings, called gravitons that can travel through the bulk, off our brain. If this is true, it could elegantly explain something that has always puzzled physicists. Why is gravity so incredibly weak compared to the other fundamental forces? Electromagnetism is about 1036 times stronger. In brain cosmology, the answer is simple. Gravity isn't actually weak. Its strength is just diluted because it's spreading out into these extra, hidden dimensions. We only feel the portion that stays on or near our brain. So when Dr. Chen's team, grappling with their inexplicable simulation results, arranged a video conference with Dr. Randall and showed her the data, the directional resistance, the interference patterns, the signature of bulk resistance, her reaction was reportedly electric. Years of theoretical work, largely sidelined by the mainstream, suddenly seemed to be staring back at her from the Azure simulation output. "What you're seeing," she apparently told them, her voice trembling with barely contained excitement, "looks exactly like what we would expect if our universe were embedded in a higher dimensional bulk space. This could be the first empirical evidence for brain cosmology." The simulation's gravitational fluctuations, the weird drag at the edges, they didn't just resemble her predictions. They aligned with eerie precision. The mathematical signature of the resistance detected in the Azure simulation matched the kind of brain tension her equations predicted, the natural resistance that would occur as our universal membrane pushes against the fabric of this higher dimensional bulk. The varying resistance in different directions. It corresponded perfectly with the predicted effects of our brain interacting with the structure within the bulk, maybe even pressing up against another, unseen brain. Dr. Randall herself reviewed the raw simulation data, poring over the numbers generated by Azure's massive computation. Her conclusion was stunning. "What's remarkable," she noted in her formal analysis, "is that these aren't just vague similarities. The quantitative values, the specific strength and patterns of the resistance, match my predictions with a precision that's difficult to dismiss as coincidence." Decades of abstract theory, suddenly finding potential validation in petabytes of simulation data. But hold on, because the implications get even more profound. The Azure simulation didn't just show resistance. It showed a large-scale asymmetry in the universe's expansion that couldn't be explained by anything inside our simulated cosmos. In one vast region of the model, expansion seemed to be slowing down more than expected, while in another direction, it was accelerating even faster than predicted by standard dark energy models. This wasn't random noise. It was a coherent, directional bias across cosmic scales, creating what the researchers started calling a cosmic flow. Think about being on a raft in the ocean. If the whole ocean current is moving you north, that's an external influence. You can't explain your northward drift just by looking at the waves and winds immediately around your raft. Similarly, this cosmic flow in the simulation seemed to be driven by something external to the simulated universe itself. They reconfigured the simulation, changed initial conditions, the directional bias remained. Something outside was consistently influencing the expansion, and doing so differently in different directions. What could cause such a thing? One interpretation straight out of brain cosmology is potentially universe-altering, brain friction. What if our universe isn't alone in the bulk? What if there are other brains, other universes, existing parallel to ours in higher dimensions? It's as if our universe is rubbing shoulders with another cosmos, explained Dr. Sophia Patel, one of Shaving's the quantum cosmologists on the team, and we're detecting the gravitational friction between them. Is our universe literally bumping into a neighbor? The data suggests that whatever lies beyond our cosmic horizon isn't empty or uniform. It has features, structures, perhaps its own laws of physics. The patterns detected resemble what some theorists call shadow matter existing on a nearby brane that we can't see or interact with directly, except through gravity. Remember how gravity might leak between branes. If there's a massive galaxy or cluster of galaxies on a neighboring brane, we wouldn't see its light, but we would feel its gravitational pull across the dimensional divide. Could this be part of the explanation for dark matter? We infer dark matter's existence because we see its gravitational effects, galaxies spinning too fast, light bending around invisible masses. We assume it's some exotic particle within our universe that we haven't found yet. But what if some of that unexplained gravity isn't from matter in our universe at all, but from shadow matter in an adjacent universe? It's gravity reaching across the bulk. The Azure simulation, showing these external gravitational influences, lends startling computational weight to this idea. And what if that neighboring universe is also expanding? Imagine two balloons expanding side by side, occasionally bumping and interacting. The complex patterns of resistance and interference seen in the simulation might be the signature of this cosmic dance, the interaction between our expanding brane and another. We might be witnessing, for the first time, faint evidence of a vast cosmic ecosystem, a multiverse where universes grow, interact, and evolve in response to each other. Okay, deep breath. We're talking about higher dimensions, universes rubbing shoulders, gravity leaking across realities. This is heavy stuff. Before we dive even deeper into what this could mean for the beginning, the end, and maybe even the nature of reality itself, I want to hear from you. What's your gut reaction? Does this sound like breakthrough science, mind-bending speculation, or something else entirely? Let me know your theory in the comments below. Higher dimensions, cosmic neighbors. Or is there another explanation for these anomalies? Hit that like button if this kind of deep science gets your mind racing, because we monitor those comments closely, and your ideas might even shape our follow-up discussions. Now, let's zoom out and consider the truly staggering implications if these findings hold up. If our universe is just one brane in a higher dimensional bulk, possibly interacting with other branes, our entire understanding of cosmic history and destiny gets rewritten. The Big Bang, was it really the absolute beginning of everything? Or was it just the beginning of our local expansion on this particular brane? Some brane cosmology models propose scenarios where the Big Bang could have been triggered by a collision between two branes in the bulk, a cosmic clap that infused our brane with the energy to expand. Or perhaps our universe budded off from a parent universe, a fold in the higher dimensional fabric. It opens the door to pre-Big Bang physics, to a history before our own cosmic clock started ticking. And what about the end? We talk about the heat death of the universe, a scenario where expansion continues forever until everything is cold, dark, and dispersed. Or the Big Rip, where acceleration tears everything apart. Or the Big Crunch, where expansion reverses. But if we're part of a larger system, these might not be ultimate endings. They could be transitions. The heat death might just be our brane reaching a state of equilibrium within the bulk. A Big Crunch could be our brane collapsing before potentially rebounding in another Big Bang-like event. Interaction with another brane could lead to merging, transformation, or a folding back into the higher dimensional structure. Our universe's story might not be a linear tale from beginning to end, but just one chapter, perhaps one cycle, in an infinitely grander cosmic narrative playing out across dimensions we're only now beginning to computationally glimpse. It suggests cosmic history is far more complex, cyclical, and interconnected than we ever dared to imagine. This inevitably leads to profound philosophical territory. If reality is layered like this, What does it mean for existence itself? Are the fundamental laws of physics we observe merely emergent properties of this deeper, higher dimensional reality? Some physicists and philosophers are already debating these points with renewed vigor. Is consciousness itself somehow linked to these cross-dimensional interactions? Could awareness be a phenomenon that isn't strictly confined to our brain, but operates at the level of the bulk? Some highly speculative theories even propose that consciousness might be how the universe, or the multiverse, feels its own boundaries, that our subjective experience is tied to the cosmos detecting its edges and interactions. Wild. Absolutely. But the Azure data, however interpreted, forces us to confront the possibility that reality is far stranger than our current physics describes. Which brings us to another, perhaps even more unsettling, interpretation hinted at by specific patterns within the Azure simulation data. An interpretation that resonates with ideas previously confined to science fiction and philosophy, the simulation hypothesis. Some researchers analyzing the Azure data, particularly those with backgrounds in quantum information theory, noticed something peculiar about the way the physics behaved at the simulated boundary. Dr. James Liu, a quantum information theorist involved in the analysis, pointed out what he termed computational cutoffs. As the simulation reached the edges where the strange resistance occurred, the incredibly complex calculations describing quantum fields seemed to simplify dramatically. It was as if the system was optimizing itself, like an algorithm designed to conserve resources. Azure's own machine learning models, trained to find patterns in vast datasets, flagged recursive mathematical structures near these boundaries that looked less like the continuous equations of fundamental physics and more like compression algorithms or error correction code. Think about the code used in quantum computers to prevent information loss, decoherence, and maintain the integrity of the calculation. The equations at the simulated edge started resembling that kind of structured, information-preserving code. It's as if reality itself becomes more efficient at the boundaries, Dr. Liu noted. Physical processes that required immense computational complexity in the middle of the simulated universe suddenly followed much simpler rules near the edge. This, he argued, is precisely what you might expect if you were running a simulation and needed to manage finite computational resources. You'd simplify calculations at the periphery where precision might be less critical, or where you're hitting the limits of your processing power. So if the universe is expanding, what if it's expanding towards the edges of its processing field? What if the fundamental constants of nature aren't truly fundamental, but are actually parameters set by the limits of an underlying computational system? Think about it. Why is there a maximum speed limit in the universe, the speed of light? Why do quantum states collapse into definite outcomes when measured? Why do Planck units seem to represent the smallest possible meaningful measurements of length, time, and mass? Perhaps these aren't intrinsic properties of reality, but the resolution limits of the system generating our perceived universe, like the pixel size on a screen or the maximum processing speed of a CPU. Now, this doesn't automatically mean we're living inside a giant video game created by some alien teenagers. The computational aspect could be intrinsic to reality itself. Professor Max Tegmark of MIT has famously proposed the mathematical universe hypothesis, the idea that our physical world is, at its deepest level, a purely mathematical structure. All the complexity we see emerges from underlying mathematical rules. The Azure findings, showing physics behaving like optimized code at its boundaries, offer unexpected, albeit highly interpretive, support for this mind-bending idea. Reality might not be in a computer. Reality might be a computation. And then came the most startling discovery of all. During the final, most intensive simulation runs, pushing the model further than ever before, Azure's AI didn't just flag anomalies, it flagged a failure point. a zone in the model where space-time expansion simply stopped. Not slowed down, not hit a barrier, but the simulation itself returned null. The team's first reaction, again, was technical limitation. They must have finally hit the absolute ceiling of what even Azure's vast network could handle. They scrambled. They double-checked algorithms, optimized code to within an inch of its life, allocated even more cloud resources. But it wasn't a hardware or software limitation. No matter how they configured the simulation, no matter how much processing power they threw at it, they consistently hit the same boundary. The simulation didn't crash. The mathematics underlying the expansion simply ceased to resolve. It was as if the model had reached a coordinate beyond which the rules of physics themselves, as encoded in the simulation, no longer applied. It's like finding the edge of the map, Dr. Chen wrote in the research notes. Not just any map, but the map of reality itself. The interpretation, terrifyingly simple. The simulated universe might be pressing up against the absolute outer boundary of its rendering space. Beyond that point, the physics engine, whether that engine is a literal computer or the fundamental mathematical structure of existence, simply doesn't compute. It implies there is an edge, a definitive limit, and the simulation had just computationally touched it. What made this even more shocking was the location of this boundary in the simulation. It appeared at a specific, consistent distance from any observer point within the model, roughly equivalent to 16.8 billion light-years in their scaled simulation. Now, our current estimate for the radius of the observable universe, how far we can theoretically see, given the age of the universe and the speed of light, accounting for expansion, is about 46.5 billion light-years. These numbers aren't the same, but the fact that the simulation hit a hard boundary within the same order of magnitude as our observable limit, especially when modeling extreme boundary conditions, is provocative, to say the least. Could the simulation be hinting that the actual edge isn't that much further than what we can already observe? Even more unsettling, as the simulated universe approached this null boundary, the expansion didn't just stop abruptly. In the final increments before hitting the wall, the expansion began to slow down asymptotically. It got closer and closer but never quite reached the edge, decelerating infinitely as it approached. Like Zeno's paradox, where you keep having the distance to a target but never technically reach it, played out on a cosmic scale. It's as if the universe knows it can't cross that boundary, one team member noted. As if there's a built-in safeguard, a fundamental rule preventing anything from reaching whatever lies beyond. This led some researchers down an even more speculative path, the possibility of a cosmic firewall, a deliberate barrier, natural or perhaps even engineered, separating our reality from whatever exists outside. Its mathematical signature, this asymptotic slowdown and null boundary, appeared consistently. So where does this leave us? Whether you lean towards Lisa Randall's brain cosmology, our universe as a membrane in a higher dimensional bulk, interacting with neighbors, or the more radical simulation hypothesis, our reality as a computation reaching its processing limits, the Azure simulation data points towards a staggering conclusion. Our universe is likely not alone and not infinite. It appears to be nested within, or bounded by, something larger, something more complex, something operating under principles that our current physics, developed solely from observations within our system, cannot fully describe. This doesn't mean Einstein was wrong, or that quantum mechanics is invalid. General relativity still beautifully describes gravity on large scales within our universe. Quantum mechanics still flawlessly predicts particle behavior within our universe. But both of these monumental theories might be like Newtonian physics, incredibly accurate within their domain, like calculating trajectories on Earth, but ultimately incomplete descriptions of a deeper reality, like relativity is needed near black holes or at high speeds. They might be special cases, approximations of a more fundamental framework that encompasses extra dimensions, cross-brain interactions, or perhaps even computational constraints. Microsoft Azure's cloud network, designed for tasks ranging from business analytics to AI training, may have inadvertently provided the computational microscope needed to glimpse the structure surrounding our reality. The simulation isn't fake. It's a mathematical model built on our best understanding of physics. And that model is telling us that the reality described by that physics seems to be interacting with, or bounded by, something beyond itself. We've potentially touched the outer wall. This isn't just abstract theorizing. It opens concrete avenues for future research, maybe even experimental verification. If our universe is interacting with other brains or a higher dimensional bulk, these interactions should leave subtle but potentially detectable fingerprints. Where would we look? The cosmic microwave background, CMB, the faint afterglow of the Big Bang. Are there large-scale temperature anomalies or polarization patterns in the CMB that don't fit standard models, but could be explained by ancient collisions or ongoing friction with another brain? Gravitational waves, ripples in spacetime caused by massive events like colliding black holes or neutron stars. Could precise analysis of gravitational wave signals reveal deviations caused by gravity leaking into extra dimensions, or interference patterns from interactions beyond our brain? LIGO, Virgo, and future detectors might hold the key. Quantum effects. Are there seemingly random quantum fluctuations that aren't truly random, but are influenced by cross-brain forces or interactions at the computational boundary? Experiments probing the limits of quantum mechanics could stumble upon evidence. And of course, the philosophical implications are immense. If our universe is just one among potentially countless others in a multiverse, whether stacked brains or separate simulations, then the range of what is real expands infinitely. Every possibility allowed by the laws of physics might be realized somewhere. Every choice made differently, every path not taken here, might exist in another universe. Our existence, our entire cosmos, becomes just one possibility realized within an unimaginably vast landscape of realities. As Dr. Randall powerfully stated, reflecting on these possibilities, we've spent centuries looking up at the stars and wondering what's out there. Now we need to look at the fabric of space itself and ask, what's beyond that? Thinking about all this, it's humbling, isn't it? For centuries, we've acted as if we were getting closer to a complete theory of everything, a final set of equations governing our universe. This discovery, or even the possibility of it, throws a beautiful wrench into that. It reminds us that the universe, or perhaps the meta-universe, is likely far grander, stranger, and more mysterious than we've ever conceived. For me, the biggest lesson here isn't necessarily about brains or simulations specifically. It's about the nature of discovery itself. It shows how unexpected breakthroughs can come from unlikely places, like a cloud computing network analyzing boundary conditions. It highlights the importance of questioning fundamental assumptions, even one as basic as the universe is everything. And it underscores the incredible power of collaboration between theoretical insights, like Randall's decades-old work, and cutting-edge computational tools, like Azure. How can we apply this to our own lives? Well, maybe it's a call to embrace mystery, to accept that we don't have all the answers, and that's okay. In fact, it's exciting. It encourages us to stay curious, to keep questioning not just about the cosmos, but about the assumptions we make in our daily lives, in our relationships, in our work. Are there invisible shorelines or higher dimensions influencing our own personal worlds that we haven't considered? Perhaps thinking about the universe bumping against boundaries can inspire us to gently probe our own perceived limitations. Are they real, or just artifacts of our current understanding? It also fosters a sense of profound interconnectedness. If our universe might be interacting with others, maybe it's a metaphor for how interconnected we all are, influenced by forces and people seemingly outside our immediate bubble. This discovery, in a strange way, makes the cosmos feel less empty and more like a bustling, interactive neighborhood. So I have to ask you again, now that we've journeyed to the edge of simulation and theory, how does this potential discovery make you feel? Does the idea of a multiverse or a simulated reality excite you, frighten you, or both? What do you think would be the biggest implication for humanity if we definitively proved our universe is part of a larger system? Share your thoughts, your deepest cosmic reflections, in the comments. I truly believe discussing these ideas helps us all process their magnitude. Thank you for joining me on this incredible journey to the very edge of what we thought was real. It's discoveries like these that remind us we live in an astonishingly complex and beautiful cosmos, with secrets still waiting to be uncovered. Please take care of yourselves, stay curious, and keep looking up, and perhaps now, looking beyond. If exploring the deepest mysteries of the universe and potential paradigm shifts in science excites you, make sure you subscribe to our channel and hit that notification bell. You won't want to miss our next episode, because we're going to dive into a related, equally mind-bending theory: our black holes' portals. New gravitational wave data is hinting at something incredibly strange happening at the event horizon, something that might be our first direct glimpse of transport between these theorized dimensions or branes. Could black holes be the gateways to this larger reality? We'll break down the evidence and the theories next time. Until then, stay safe and keep questioning everything.